Okay, so we're looking at the remainder theorem today, which is going to basically give us a faster way, first of all, faster way to get the remainder if we're doing a division, but it's going to lead us into the factor theorem, which will be tomorrow. In any case, it's a good way to, these first two questions, to review synthetic division. So if we're dividing f of x by x minus 2, we're going to do it by synthetic division. So remember, bring down the 3, multiply through, and then subtract. Okay, so this is your remainder. Okay, then we want to try to see, math is all about patterns. What happens if I substitute 2 in for f? Obviously, we're leading you towards something. So 24 plus 20 plus 12 minus 4. So 44, 56 equals 52. Well, that was the same as the remainder when we did synthetic division. So is it equal? Yes. Is this only a coincidence? Let's try another example. So then here, g is divided by x plus 3. So, same thing here. Right, and that's your remainder. Okay, so we've done 2 examples with synthetic. Then now we're going to substitute negative 3 in. Notice that the value negative 3 is the value that makes this binomial 0. The value 2 up here was the value that made this binomial 0. Okay, so that's going to help us. So let's go back and finish g of negative 3. Negative 8 minus 15 minus 7. So this was the remainder in your synthetic division. And that's the value that we got when we substituted negative 3 in. So where do we, in both of these, we told you what to substitute in. So in B, you have to substitute in 2. Got the remainder for when you divided by x minus 2. This one, we told you to substitute negative 3. We got the remainder, the same value as the remainder when we divided by x plus 3. So how do you decide what to substitute in to the polynomial to get the remainder? Yeah, opposite sign, exactly. So opposite of positive 3 is negative 3, okay? Or you can think about it as whatever value makes this 0, right? If there was, so that's either way, okay? As long as it's an x plus something or x minus something. Remember, we can't use synthetic division when it's degree 2 or more than 3 terms. So it's not going to be, we're not going to be able to get the remainder for all types using synthetic, but it will give you the remainder, again, linear functions, because we have to substitute in by that constant term. Okay? So this, again, yes. Are you convinced now? Well, it's only 2 examples, but hopefully you can kind of, we can convince you. So it is a theorem. It has been proved. So theorems always have been proved. And we're not going through the proof, but when a polynomial is divided by x minus a, the remainder is equal to f of n. You just take that value, opposite sign of that constant term, substitute it in. So the remainder when f of x is divided by x minus a can be determined by evaluating the polynomial function at x equals a. That's exactly what f of a is doing. Vice versa, so f of A can be determined by finding the remainder when f of x is divided by x minus a. Kind of like a biconditional statement, either way. So if you know f of a gives you a certain value, then you know that value is the remainder when you're dividing by x minus a. Okay? So this is going to be helpful in cases where we don't care about the quotient. Okay? If you just want the remainder, then why bother going through all the synthetic division or through all long division? If all we want is the remainder, way easier just to substitute a value in. You don't have to do a chart or a diagram. You don't have to think about what the coefficients are. You just substitute and follow order of operations. So it kind of makes things easier depending on what you're asked. Also, it leads into tomorrow's lesson about the factor theorem, because if your remainder is 0, that means that that divisor goes in evenly. And so it's another way for us to be able to factor bigger polynomials, because we can then know that x minus a is a factor. So it kind of leads in to tomorrow's stuff. Okay, so write a conclusion given the following statements. When g of x was divided by x plus 5, so we don't even know what g of x is, okay? But when it was divided, the remainder was negative 12. So that means that g of negative 5 equals negative 12 by the remainder theorem. Okay. Opposite sign of the constant substituted in gives you the remainder. Okay. So this means here, this is like this statement, so now we're going backwards. That means when p of x is divided by x minus 6, the remainder is negative 17. Okay? So they're either or, vice versa statements. Okay, so next one says determine the remainder when f of x is divided by x plus 1 by using synthetic division and the remainder theorem. So doing it both ways. Okay, so getting that practice for synthetic division is important because you will need to know synthetic and use it as we go through this unit and next year and in calculus, etc. So you get the same thing again. So that's a third example of showing that when you substitute the value for x that makes that factor equal 0, you get the remainder. Okay, so as I said, sometimes you're just going to use the factor or the remainder theorem. Sometimes you're not even going to bother because you need to know the quotient. So it really depends on the question. So ones where you don't really need to know the quotient are ones like the next one. So when p of x is divided by x minus 1, the remainder is 7. So it's telling you what the remainder is. determine the remainder when p of x is divided by x plus 2. So notice here that we don't know what k is. Okay, so we do know what the remainder is when we're dividing by this. If you do synthetic division, it will work, but it'll be a messy solution and guaranteed students make a mistake. Because really, you would have, say, a k here, and then you'd have to follow down with the k's and oftentimes add or subtract incorrectly. That's why the remainder theorem is easier. So this is saying that p of 1 equals 7. Okay, that's what this is saying. So now find what p of 1 is in terms of k. So p of 1 is 1 cubed plus k times 1 squared plus 2 times 1 plus 9, and that's equal to 7. And solve that for k. Then you can go back, put it back into p of x, and find p of negative 2. So therefore, our p of x equals x cubed minus 5x squared plus 2x plus 9. Okay. And so now we're going to find the remainder here will be when x is negative 2. And evaluate that. So that's the remainder. Next one's very similar. G of x this time. When it's divided by x minus 1, remainder is 4. When it's divided by x minus 2, remainder is 21. So you're told that. In this case, you'll notice in g of x, there are 2 coefficients that we don't know. So just by doing the first part, we can get an expression in terms of k and p, but we can't solve for each of them like we did in the last one. We could solve for k. So that's why we need 2 pieces of information so that we get 2 equations in 2 unknowns. Okay? So we want to find so remainder equals g of 1. Okay, so the remainder here is 4. G of 1. Substitute 1 in for every x. Then we're going to do the remainder equals g, well, actually, you can just put 4 in here, right? 4 is the remainder. Oh. remainder is 21. And that's going to be 2. So then you'll have 2 equations and 2 unknowns that you want to solve algebraically. I'm just going to get the k plus the k's and p's on one side. Divide by 4. And then solve that. So that's going to be -3, negative k, so k equals 3. And then substitute that in, and 3 would equal -1. Okay, then you could check, right? Let's check actually. So go back, go in your calculator, you could graph your function with these values. So y equals, that's going to be 3x cubed minus, minus 1x squared, so minus x squared, minus x plus 3. Let's just do a standard screen, standard view there. Okay, so when x is 1, we should get 4. So trace, punch in 1, x is 1, enter, we get 4. Okay, so that's good. Then also check x is 2. So trace 2, we get 21, and that's what we got there for our remainder. So you know you found your x, your k and p values correctly. You can check back with your calculator. And that's it. That's the remainder theorem.